I've been indeed working in the technical department of Vortex for almost 20 years right now, and through all the products that we've been developing for wind resource departments, I'm very happy to present here today our last product times that has somehow that summarizes a little bit a lot of efforts in which we have been able to generate long-term time series that at the same time are high resolution, which seems obvious, but it isn't. So I'll try to explain the reasons why we were after this product, why the reasons why that motivated us into developing this, and then how we managed to develop so, and of course, a lot of validation metrics and guidelines on how to use the product and how it can be useful in your departments. And of course, some conclusions and takeaways, recommendations. So for those that are familiar a bit with the modeling world of wind data, there is always a dichotomy between generating long-term data sets and high-resolution data sets, because if you want to go into long-term data sets, then they are of interest because you need the long-term, but then if you want to generate high-resolution, it's very expensive in terms of computational cost. So traditionally, a lot of models, when going into high resolution, they tend to be short on time or even sector-wise only. And on the contrary, if you want to generate long-term climatic data sets, then you're able to generate them somehow easily through mesoscale modeling or reanalysis data, but they are not high resolution. So we wanted to, let's say, join both worlds. So we wanted to generate data sets that are both mesoscale long-term climatic descriptive and at the same time high resolution microscale. So that means high frequency 10-minute data with a lot of variables describing the turbulence, describing the variability of the data, and so that they are useful for the AEP estimations and other applications in the wind industry where you really need the high resolution, speed up factors, etc., etc. So the challenge was to generate the both of both worlds, so long-term mesoscale and short-term microscale, to put them together and see if we were able to generate a useful time series. So that's a little bit what we wanted to generate. So that's the final picture, the final deliverable, right? So we want to generate 10-minute data sets with a lot of variables, specifically wind speed, direction, and also standard deviation that describes turbulence, and a lot of meteorology that can be used for stability, wakes, etc., and that cover 20 years. So how to do that, right? So here is a lot of efforts in our technical department. Somehow we were designing the product in order to make it possible. And what we did is, for those familiar a little bit with Vortex, we are let's say our engine of a generation of wind data is the WRF, the Weather Research and Forecasting Model. We use ERA5 as an input condition, but of course, we cannot run WRF at high resolution for 20 years because then it will be very, very expensive, and the product will not be affordable. So how to do that? Well, what we decided is to go into to run two separate simulations. On one hand, we run a WRF, what we call a baseline simulation, that will cover 20 years explicitly. And we are generating a pretty high resolution, not super high, but still pretty high, which is 300 meters. And we are able to generate 10 years of data with a 10-minute output. The key thing here is that even though it's 10-minute output, it's not fully descriptive of microscale, because in the WRF model, you can choose to parameterize the microscale with the boundary layer parameterization, surface layer parameterizations, etc., where you can save a lot of computational resources. And you get a very nice descriptive climatic time series, which somehow is missing a little bit of microscale details. But on the other hand, we can run a separate simulation which uses the WRF LES technology. It's a technology that it's included in the WRF model. It has an incredibly higher computational cost compared to the default WRF simulation. But the good thing is that it solves the equations explicitly. So any turbulence and phenomena is explicitly solved in an Navier-Stokes equations. And that makes it possible to generate, let's say, a very, very high detailed simulation, but only for a shorter period of time. So the ideal situation would be to run WRF-LES for 20 years, but this is not possible really in terms of affordable cost. So what we decided to do is, okay, let's run one simulation for 20 years on one hand, and then a separate one for the same location for a shorter period of time. And then why not combine both of them in a, let's say, a sort of MCP between model techniques, okay? So what we do is we try to take the WRF-LES, let's say, richness in order to improve the 20 years previously generated where WRF is not perfect, let's say. So we try to learn from the WRF-LES what is the wind distribution, how is the wind distribution in WRF-LES, and we try to also understand the turbulence and also understand the sub-hourly variability that the WRF-LES is showing us. We trust the WRF-LES, and then we try to trespass, thanks to some machine learning algorithms. It's, let's say, you could say it's an MCP between models, okay? Instead of learning from measurements and try to extend, improve the model, we let's say, use the WRF-LES as if it were measurements, okay? And then we learn about the WRF-LES and improve and enhance the previous 20-year simulation. The good thing about this is that you can save a lot of computational resources, and still we will see in the results that the improvement in the model WRF baseline, it's pretty acceptable, and results show really usefulness. Usability, sorry. So, and a little bit what we get from it is, this is just a snapshot of a comparison between measurements and our times product for a 2-day evolution. I think this is it. You can see here that thanks to what has been learned from the WRF-LES, we can see that our times product, which is the, let's say, the pink or red line, it has a lot of texture. It really describes the reality in terms of a spectral behavior. So, and this is also the vertical levels of the model. You can see that there is a lot of things going on here. Really, the model is able to understand that something is happening. Of course, this is not a comparison against measurements, just a preview of what the model can do. And the good thing is that now we are getting something realistic, apparently, but of course we have to check whether this is good or not in terms of accuracy. So we have to go into validating the results. And I think that my colleagues in the technical department did a very nice effort last year. They selected almost 300 sites distributed worldwide. All of them are located in wind energy relevant spots. So there are no meta stations here from airports and so on. So everything is 10-minute data at least 1 year, and high met max data at least 60 meters or more. So we picked up all the sites, and then we basically run 1 year of our product times, or more than 1 year, if possible. And then we want to check several things. We need to check, is it really accurate in terms of microscale classical metrics in the wind industry? Well, let's check it out. What we did is, for the 300 sites, almost 300 sites, we have a very clear summary of metrics. This is the main one, probably. This is what you could call the error, speaking quickly, this is the quick metric that summarizes the error. This is on the order of 5 to 6% of error in the deviation of the annual mean wind speed estimated by our product times for the whole portfolio of sites. This is pretty good, I would say. And also the standard deviation is quite narrow, which means that there are no very relevant outliers, which is good, because then you can trust the product, let's say, even though you don't know anything about the site, okay? There is no bias in the model. This is not anything new, I would say, because the WRF model behaves pretty much like that in many resolutions. So that means that the model has no tendency to overestimate or underestimate. And of course, there are some relevant metrics in terms of the 10-minute scales about correlation, pretty relevant value, 0.70 on the Pearson coefficient square value on the 10-minute scale, which is quite interesting. So results look good, but how about the results in terms of terrain complexity? And today we are focusing on offshore. Here you can see the 272 sites. They are split here in types of terrain. By the way, this document, and a more extensive one is available on our website if you are interested in this. And you can see here that the value that I was referring before of about 5 to 6% of error, you can see here how it's distributed in terms of categories. It is very clear that when the terrain complexity increases, then you get more outliers, which makes sense because if there is a lot of complexity in the terrain, then strange things can happen when cross-checking measurements and the model has more difficulties. And for example, for offshore, in terms of correlation on a 10-meter scale, very super high correlations in the 10-meter scales for the offshore sites. You can see here in blue. Okay, so this is interesting. And also for the root mean square error, the offshore seems to be really, really accurate, which makes sense. But still, it was good to see that indeed the times product was doing that on a 10-minute scale. So we were pretty satisfied with this 10-minute, let's say, metrics in terms of microscale descriptive. But if you think about it, there was nothing here very, very new compared to hourly data sets because everything was averaged. So is the fact that it's 10-minute useful in some other sense? Oh, let's check, for example, the extreme wind speeds, which is something that you cannot probably analyze on an hourly data set, because you really need the 10-minute thing, because it's the rule on the Gumbel feed and the standard procedure for determining the extreme wind speeds, right? So somehow you are obliged to do that on a 10-meter scale. So what we did is from the 300 sites, we were able to select about 30 that had more than 8 years of measurements. There was a limitation because, of course, for the extreme wind speeds, we need at least, let's say, 5 or 10 years in order to derive the VREF at a 50-year return period from the measurements, not from the model, but just from the measurements, right? So, we can generate our times product for, let's say, 10, 20 years, and at a reasonable cost, thanks to this enhancement with WRF-LES. And we are able to generate 10-minute data sets that cover long periods of time, and then we are able to extract the annual maximum wind speed and then perform the Gumbel feed, which is, I would say, one of the most standard weights to generate an estimation for the VREF. Okay, you can see here, this is an example of one site. This is a VREF estimation on a 50 return year period. You can see here this 40 meters per second from the measurements, and this red line is what we get from the times product. Well, it's not perfect, it's underestimating, but still it's a pretty good fit. And for all the 30 sites, we were able to reach a nice value of, let's say, 11% of deviation when estimating our VREF. Interesting to see that our times product was never designed for VREF estimates. It was just a generated 10-minute long-term data set. And when you go into analyzing it, it does a pretty good job when analyzing extreme wind speeds. So yes, we were happy. This is also 10-minute descriptive, and it's useful because some other data sets are not useful for this if they are not 10-minute, okay? But then there are more things. We also want to check, is it useful for other things? For example, stability. Is it useful for detecting low-level jets, inversions of profiles, negative shears, and strange veer behaviors that can be used for, I don't know, sector management, curtailment, etc., or wake analysis? Here there is just a quick snapshot of what the model output can look like. This is no measurement comparison, but for example, here you can see several vertical profiles. Here there is a nice one. This is the diurnal cycle every 3 hours. For the data set, you can see that, interestingly, the model is able to see that this site has a very different behavior at nighttime or compared to daytime, for example. And you can see here the generation of low-level jets, which is something that in a mesoscale, medium resolutions, it's a little bit more difficult to get, almost impossible, I would say. But when you go into this high resolution combination of WRF LES and WRF baseline for 20 years, you can really get them. This is interesting, right? You can also see some VIR examples, etc. So the data sets look like a powerful tool in terms of meteorological variables. And also something that we cannot forget, and is very new in these times, is, we have the ability to check the standard deviation on a 10-minute scale. This is relevant because you can really plot the turbulence intensity, which can become very useful for offshore, for example, when there is a very, I would say, scarce availability of measurements from lidars, which turbulence is not very well measured, and met mass are not very affordable in offshore. So can we check the turbulence intensity from our times? Yes, why not? Here is an example of the turbulence intensity curve for 1 year as an average. This is the comparison between measurements in black and the vortex times in this red-pink color. And well, what we did is for about 100 sites, which was the number of sites where we had measurements of turbulence available, we were able to cross-check, let's say, some metric that tells us something about the distance between the curve between our times and the data. There are more metrics available on our website, because I would say that there is no standard metric of turbulence intensity. So somehow we tried to measure here the distance between the curve. This is in percentage of the distance between curves, but there are more metrics available on the site, on our website. So I invite you to cross-check them. So it looks like this times product is useful also for estimating the turbulence. And I don't want to extend a little bit more. I want to go to conclusions, but for those interested in stability, the model is able also to generate Monino-Volkov length information, Richardson number information, and of course, other diurnal cycles that can also be of interest. For example, heat fluxes and so on, they are also available as an output in the times product. So it looks like indeed this times product looks like a useful 10-minute long-term high-resolution product that can be used in the wind resource departments in order to complement the wind resource analysis in different aspects. Of course, it will depend depending on every user, but it looks like a useful tool. And it's also very satisfactory to see that the WRF LES run for a shorter period of time has been useful to improve the whole long-term period of 20 years. And we saved a lot of computational resources, which makes it then affordable for the users to download this product at a reasonable cost and time. And there is more. There is more coming probably this week about a tool that will combine. It's a tool that a calibration tool available in our platform called times remodeling, similar to our series remodeling. Those familiar with it, you may already know that we offer these for series, but in this case, the times remodeling will allow a 10-minute output for 20 years by combining measurements and our model, the times product, at a 10-minute scale, including turbulence, which is very, I would say, new in order to extrapolate turbulence to the long term for those having measurements of, I'd say, 8 months of measurements of turbulence, and then you want to extend to the long term, etc., etc. So I think that will become available this week in our portfolio. So I also invite you to test this tool when it's available, and I'll be happy to take questions at the end. Thank you very much.
Thank you, Paul. It was very interesting. We have some questions now, so maybe we can answer a few of them now before Edvard started. And then maybe you can the rest of the questions you can write them, so you can answer them writing the answer directly in the Q&A section. But for example, someone is asking if you have seen variation in model performance in different regions. I would say we have done this validation for different terrain complexity but which we think it's more interesting than different regions. But we understand that people is interested in how the model performs in their country or in their regions. Can you say something about this, Pau?
Yes, indeed. This document, of course, summarizes the whole world together and only split it in categories, as Patricia mentioned, in terms of terrain categories. But we are also able to generate, of course, depending on the region, because of the measurements availability, but we are able to split this information in countries, for example. And if for some of the countries, we are also able to split them in terrain categories within this country. So I think that there are some documents available on the website, but in case that they are the specific country or region that you are interested in is not, just let us know, and we have let's say a good database where we can summarize the outputs. Of course, we cannot make available the location of the measurements, but still we can provide a nice summary for some regions. So yes, we have split them in different regions, countries, continents, depending on what you need.
Okay, thank you. And someone, two people is asking about if we have considered the 6 month periods from work LES. Why 6 month period and not one year period? If we have seen any difference between choosing 6 months instead of 1 year, and why?
Yes, that's a very expected question, I would say. Well, there was a lot of sensitivity tests internally when building up the product, developing the product. Well, of course, the main purpose was to generate a work LES simulation as short as possible in order to save cost, but at the same time, the minimum necessary period to make it, let's say, compatible with the extrapolation, right? And the 6 months really showed that it was more than enough. There has been a lot of questions about this, and why not 1 year? Well, the question is because it has a double cost in WRF-LES computational resources, of course. But I would try to summarize very quickly that this is not the classical problem that we have when comparing measurements and model, where of course we all know that using only 6 months of data to extrapolate to the long term will be a problem because of seasonality. At least you need, you say, 1 year. That's the standard accepted thing in the wind industry. But this is a pretty different thing. Why? Because this is not measurements against model. This is model against model. And the two models are initialized with the same boundary conditions, with it, which is R5. So that means that you will be incredibly surprised to see that the correlation between WRF-LES for 6 months compared to the standard WRF baseline for the 6 months coincident period is incredibly high. So because they are two models, both of them are downscaled in the same technique, except for the WRF-LES part, which is in the end of the modeling chain. So you don't need to learn anything about seasonality. Seasonality is already included in the WRF baseline as it is coming from R5. But WRF-LES and the WRF baseline, they do not differ depending on the seasonality. That would be the summary. So you don't need 1 year. Okay, but if you have further questions, please send them through and we'll try to send you more technical details on this.
Yeah. Okay, thank you, Pau. So I will say let's continue with Edvald's presentation, and if we have time at the end, we will answer more questions that you already wrote here. And if we don't have time, we will send you the full document of Vortex times and the validation, and there is a lot of explanation about the product there. And of course, you can also send us an email and we will be very happy to answer all your questions. So thank you for your questions. And Edvald, are you ready?
Yeah, thanks a lot for this, Pau and Patricia. And thanks, Pau, for explaining these details. For the looks of it, doesn't look like we're in the same city. You're in a quite heavy jacket. I'm still in t-shirt here in the Nordic side of Barcelona, but happy to see it looks cold from your standpoint. Just first of all, yeah, sorry that James could not attend today. I will try to keep up with his accent and explain as good as he explains the time series part that he's been developing over the last few weeks. It's quite an interesting discussion also to have. But also just to touch a little bit upon what Paul was mentioning here, which is quite important regarding Times product that you have developed. When we're doing an evaluation on early stage projects, there's always a discussion on, is it a potential site we can use for a Weibull distribution, or do we need to use a time series? And what about the TIs, which is of course a very important input when you're doing the evaluation of wake modeling, and how both internal and external wake models will impact the overall wakes of the project, no matter what the wake model you will choose at the end. So it's a very good product you have designed there, and actually that's something we will discuss during this short presentation of how you use the Vortex times in the Youwind application. And that's also, despite this very detailed technical explanation of the product, we also want to make sure that how easy it is to use and implement it in Youwind. So that's also one of the purpose of our application is to simplify the process of these complex data sets. So today we're going to view slightly how you can import these data sets from the Vortex data that you have potentially purchased or applied from their platform, how you can integrate it into Youwind, and how you can use it directly and compare how the different products actually operate, so you can have a better, broad understanding on not only the wind resource, but also on the different inputs on that you would need to calculate gross, net, and the overall cost of energy for the different sites. So just to highlight here, so if you would have a login into the Vortex platform, you can click anywhere around here and essentially jump into the Youwind platform and create a scenario directly. And all the runs that you have from Vortex actually are already part of your possibility to import into the scenarios in Youwind directly. So by simply logging into the API of Vortex through Youwind, you can also import these data sets, and that's basically what we'll do today. So we're looking into Italy, southern Italy, for a reason. It's a market that has been developing quite rapidly over the last few years. There's quite many developers that are having projects in the region, many of which are already implementing a few floating ladder campaigns. And as Paul also mentioned, floating ladder campaigns or ladder campaigns and even MetMast are an expense that is something that the developers need to account for before making a bankable wind resource assessment. But perhaps there's something in between, like this product, that can give an even better picture on how the evaluation can be from a wind perspective. Because as you can see from here, the site we're going to look at is just coming off, the wind is coming just here on different direction, is coming from the shore as well. So it's one of these items where you need to evaluate, is a possibility to use a global wind atlas or a simple ERA5 time series to evaluate the viability of this wind farm, or need to go into more detail because of there might be a very differentiation here between a typical Weibull and a time series. So basically what we've done here is that I've implemented the project here for these two regions, and we're going to compare how with this area and the overall LCOE be if you're just using a simple Weibull distribution. And the simple Weibull is something we also got from the Vortex maps. If you would just then import a simple ERA5 time series from, let's say, Copernicus or other source that you might download it for free, and just to the south of the site, how would that impact the frequency distribution of the site? And then lastly, we'll compare this with this Vortex times product that has a 20-year time series at 10-minute timestamp, and how would that impact the overall, let's say, the detailed scenario. So by just jumping into the Youwind platform, this is just some demos I'd like to show you here. So whenever we have an evaluation of, let's say, early stage project, we can also use the platform and seeing where the areas are exactly. I'll just jump and show you. For example, this is the area that we're looking at. This is a site that we just imported to start evaluating and comparing these time series with the Weibull distribution. We can simply say here which sort of wind resource we want to use. What wind resource is it that is available at the area, or what Vortex runs have I actually made accessible for this project. And here you can simply, by choosing the turbine and going into this setup here inside Youwind by saying, I would like to generate a layout using this particular area and this particular turbine. I can also choose to see which sort of wake models I would like to use. Or I can actually have a weighted average between the wake models. So whenever I do that, I can just generate a typical layout, and I'll just show you how a layout that has been applied jumps into here. So we have already a turbine layout, and we want to make a comparison between not only how the wind resource interacts between this comparison, but also how the wake losses are in comparison. So the internal wake losses in this aspect. If then you would also like to compare the external ones, and that's also something that is quite an important one, is that it's also possible to make sure that you can include these and add the external wake loss, the neighboring wind farms to calculate the external wake loss, and also do it per scenario. So meaning that if you're evaluating which wind farms comes online at what time. Looking at this site, so if you just look at a typical windrows, as you're mentioning here, you can see that the wind is basically coming here from onshore, and this might imply that there is a lot of potential for interference between the wind. So a typical Weibull distribution might not be a key for usage for this particular area. So this is what we're going to use for comparison. But anyhow, we do already have a layout, so we know more or less what is the wake effects, what's the mean wind speed at the site. And just to show also how you would use Youwind to complete the evaluation by using a Weibull distribution, is also possible to add the other technical components that you might need for evaluating these. This is a floating wind farm. As you can see here, it has a symmetry of close to 1,000 meters. And so what Youwind also does is calculating the mooring line lengths and the overall different cable distances, also not only for a static cabling, but also for a dynamic one if this is offshore. So if we would then build up this scenario by adding the onshore substations, the offshore substations, the export cables, and then the array cables, it's actually quite easy just to combine the different aspects into Youwind here, and then you can also simply generate the array cables by simply clicking a button, and you will essentially optimize the electrical cabling. It's just to show how easy it is to finalize the evaluation. And by doing this, normally what we use, if we're doing very early stage screening, is that you're using the Weibull distribution by having or mesoscale map that you would have, for example, from the Vortex data sets. So this is the typical map product that is possible to use. And normally in let's say an early stage process, when you're doing these scenarios optimization, you're trying to screen which area is more interesting than the other, then you're trying to find out what is the overall wind speed as an average, what is the bathymetry, how far are you offshore, how far you are to the grid, and you try to minimize any other restrictions that you might have, both human and environmental restrictions. And there you come up with an area that you then start optimizing the overall layout. So that's sort of what we are trying to show here, how that works. Going to the next round, this is a Weibull distribution. So what happens if you then input a typical time series? So you go back here by clicking adding a wind resource. You can also use a wind resource grid data, so a farm product from Vortex you can add. And this here I added a typical time series you get from Euro 5 just at the south of the site. By adding the time series, I can also get, let's say, the different inputs on how does this evaluate for not only for daily variation, but also for seasonal. So by importing the time series after logging into the platform, I can see basically what are the monthly means of the distribution for the typical layout. I can also add what is the data, where is the height coming from the data. So it's also possible to extrapolate that, but only not only for horizontal, for vertical, but also for horizontal extrapolation. And you can see basically here how the gross and the wake production are per month for this particular sites. You can also add here, and this is also something that we use quite frequently, something that we've worked quite hard on evaluating. So if there is a possibility for curtailment, or if the developer wants to evaluate what sort of overplanting or underplanting scenarios they want to see, so then it's possible to go into the very detail of saying, if there's a risk for curtailments or the maximum cap on export capacity, it's also possible to go even down to 10-minute average using the times product and evaluating what would that impact on the overall efficiency of the layout. This all applies to if you would have 1 offshore substations or 2 or even 3, and the type of export cable capacity you might have. Then you can also simulate that if you have HVAC or HVDC, depending on how far offshore you are. If you want to optimize for shock reactor, both onshore and offshore, it's also possible to go into that detail. By then evaluating what is the time series average per day and time series average power per day, both weight and gross, you can also jump into here and see the daily variation and seasonality. This is extremely important for a development perspective for different markets, because you want to see when does the off-taker expect the power coming on grid. So it's not only looking at the type of production per month, it's also needed to look at it per day, how the potential offtake will be. So when the developer is doing power purchase agreements with an off-taker, this is one of the first things that is possible to generate. They have to know what is a P50 time series, including all the losses, electrical losses, etc. That's exactly what we can produce here in terms of looking at the data sets. So by looking at this, it's also interesting to see if you're looking at a P50 AP, you can see here the differences between, let's say, based on a time series and based on a Weibull distribution that we have. So you can see already here, when you're taking the loss into account, that the time series here for the 0.5 data sets is showing quite a lot lower P50 value when you take it into account, and that comes for a reason. So by adding then here, I just added, this is the time series that we were adding on for this particular site. And now just to jump into here, when we're doing this sort of comparison between scenarios. So this is, if we jump into the Youwind platform here again. So for the same layout, for the same setup of turbines, same setup of foundations, cables, offshore substation, etc., we can basically jump into and add the scenario here to compare side by side. And what we want to compare here is essentially the overall production. We start with that, so that we can go into the wake modeling. The production, basically here you can see that for a typical Weibull distribution, that the wind speed 7.8 here, and we're looking at 0.5 time series and the Vortex times, the wind speeds are quite similar. But this particular area here is something that you would like to see in comparison when we're adding, let's say, a time series. So we can see obviously here, only looking at the 0.5 time series is not very Weibull site. You can see here that the wind speeds are actually higher here, or the frequency is higher for a bit higher wind speeds. And actually, if you would then add a Vortex time series, which basically looks like this, it looks a little bit more like an actual measurement at the site. We're actually seeing that for lower wind speeds, you will have the higher frequency. And this is actually quite important when you have a low wind site where you try to evaluate that you need to make sure that you're capturing the frequency distribution at the right wind speed. So you can see here the differences between the Weibull distribution, the 0.5 time series, and the times product, that essentially is showing what are the difference and how close you can come to an actual measurement when you don't have that on site. And that's why I'm praising Pau for adding this product, because what is actually quite important, as you can see here, looking at this graph, is that for this particular project, it might be only looking at the Global Wind Atlas and some high-level mesoscale maps. It's not representative of what it might be in reality. So also one of the aspects that why Youwind is very important for Youwind to import this product and use that directly for users, is to make sure that the reality, make sure the measurements or the optimization that you have for the layout design is as close to reality as you might get before you set measurements. So essentially here you can see also what's the impact on the gross. So the impact on the gross, you can see already here, is despite the similar average wind speed, but the gross is actually higher for the Vortex times, essentially because you're actually producing more on the lower wind speeds here that you can see. And it's not as spread as for the Weibull distribution. What is also interesting, if you go into here, is that we're also seeing by using this, you will have actually a higher efficiency on wake modeling. So this wake model we use here is NOE, but the same will apply when we do the testing with using TurboPark and eddy viscosity. That actually with this, for this particular project, the wake efficiency has increased here. That is actually quite important to evaluate by comparing with a Weibull distribution, and even on ERA 5, you can see the difference here between the two measurement points. And all this essentially feeds into if we're comparing the overall cost as being the same. So if we would evaluate the same cost between the models, then we can also say that, yeah, if we're looking at a capex of around 4 million per megawatt, just as an average. This is obviously a low wind site for floating very deep waters. So essentially, the LCOE would be quite high when you're comparing it to a fixed bottom site in the North Sea, for example. But the relative comparison between these is quite interesting, because when you're having an LCOE of this 196, it actually increases quite a lot when you're looking at an ERA 5 time series. So both these are actually showing quite a high LCOE initiative. But when going to the details, then you will know in more, let's say, with higher accuracy, what could the actual LCOE be for this particular site without having measurements. And you can see already here the difference between the Weibull distribution from 196 down to 189. Now, it's not always sure for all scenarios that this will be the case. That will be lower, but you will have essentially a lower LCOE for this area because of the frequency distribution. You know more or less how, and as been described here, how the standard deviation and the bias is on the measurements, which ultimately will result is the overall uncertainty on wind speeds will be lower. So that also takes into account that potentially your P90 will be higher as a result of it, which is also extremely good input for the developers that need to evaluate the projects, not only for an LCOE perspective for applying for a bid or a PPA, but also for the project finance. So this is one way of reducing that uncertainty, and you can see how big of an impact this has when we are adding these two products. But essentially, this is what we wanted to show you from the Youwind platform today. Obviously, we can go into more detail in optimizing the bid price from this particular perspective. But I'll stop here and invite everyone to contact us for more details if needed, and how we can actually go into evaluating and optimizing this. So we could potentially now, Patricia, take some questions or.
Yeah, thank you very much. That was very interesting. I would like also to introduce Ana Rivera, who is the Youwind CEO. And I think she's going to, there is a few questions for you. Maybe Ana can help me to read them, or even to answer them, or
Definitely.
you and
so let's get
Hi, Ana.
Hi there. Hi everyone. Here Ana Rivera, CEO and co-founder. Thank you so much for attending this webinar. So that we'll start with the first question, which is, it is possible to see the impact of using different wind resources on LCOE and Youwind as well?
Yeah, that's possible. We use different. You can add different wind resource for different scenarios, and you can also run that in parallel by comparing with different wake models to have the overall scenarios set. So you can basically set everything as fixed type of turbines, number of turbines, etc. But then obviously can play with the metrics as such, and then that's basically just quite common when you're doing the early stage screening, sort of where you are in terms of uncertainty between the scenarios.
Perfect, thank you so much. And then when it comes to the different wake models that we offer in our platform, can we actually control the weight that each wake model has in our platform?
Yeah, that's possible. You can basically set the percentage you want or the weighting you want for each weight model. And so if you have, let's say you want to compare pessimistic versus optimistic weight modeling in your opinion, then it could also possible to have a weigh-in of that for the overall results, and also have a sensitivity on these.
Perfect, thank you so much. And then there is one question that is asking if it's possible to, once you're using the Youwind platform, if it's possible to download the summary comparisons from our platform in order to be used in-house inside for the clients.
Yeah, that's also possible. You can download a CSV or a PDF report. It's also possible to have an API directly from Youwind to a Power BI or other server that any company is working with. So it's possible to dump the data sets also for the comparisons that many companies are already sort of utilizing, but both possibilities are available.